Hello friends, I welcome you on my channel Engineering Mathematics djganit. Today we are going to start new topic known as beta and gamma functions. So these beta and gamma functions are special type of functions which we are going to define using improper integrals. So beta and gamma are special type of functions which we can define in terms of improper integral. We cannot define these two special functions in terms of elementary functions. So first we will discuss in this lecture. We will start with gamma function and we will see how it is defined in terms of improper integral, and also we will discuss two other forms of gamma function. So gamma function is defined using improper integral. So suppose we consider improper integral of e raised to minus x times x raised to n minus 1 dx from 0 to infinity. Then this is improper integral of first type because upper limit is infinite. Now if we consider here there are two variables x and n, and we are integrating with respect to x. So after integrating, suppose this improper integral is convergent, then after integrating with respect to x, whatever we will obtain, that will depend on this another variable n. So we will get function of n for those values of n for which this improper integral is convergent. So this improper integral, if it is convergent, then it is a function of n. So this function of n is known as gamma function, and because it is a special function, it is denoted by gamma n. So this is the notation for gamma function and is defined in terms of this improper integral. So gamma n is nothing but integral 0 to infinity of e raised to minus x raised to n minus 1 with respect to x. And we can show that this improper integral is convergent if this n is positive real number. So for n negative and 0, gamma function is undefined because this improper integral is divergent if n is less than or equal to 0. So gamma function is defined if this n is positive real number. So we will remember this definition of gamma function. If n is positive real number, then this improper integral defines a function of n known as gamma function, and it is denoted by this notation. So first we have written the definition of gamma function. If n is positive real number, the improper integral 0 to infinity e raised to minus x raised to n minus 1 dx is convergent and defines a function of n known as gamma function, and it is denoted by gamma n. So gamma n equal to integral 0 to infinity e raised to minus x raised to n minus 1 dx, and this improper integral is convergent if n is positive. So we will consider gamma function for positive real numbers only in our course. We can extend this definition to negative real numbers also, but that is out of scope of our course. So we will strictly consider gamma function for positive real numbers only in our course. So and we will remember this formula for gamma function. Gamma n is given by 0 to infinity e raised to minus x raised to n minus 1 dx. So using this definition, we can prove that if we consider n equal to 1, then value of gamma function at n equal to 1 is 1. So we can use definition. We know that first we write gamma n equal to 0 to infinity e raised to minus x raised to n minus 1 dx. This is by definition of gamma function. So we are interested in value of gamma function at n equal to 1. So we put n equal to 1. Therefore gamma 1 is nothing but 0 to infinity e raised to minus x, x raised to 1 minus 1, that is 0. So this is nothing but improper integral of e raised to minus x from 0 to infinity. And this we can use the definition of improper integral. It is improper integral of type 1. So we replace upper limit by t and we consider t tending to infinity. So by definition of improper integral. So this is now integral is minus e raised to minus x and x is from 0 to t. So let me complete here. So this gives me, this is limit t tending to infinity. Upper limit is x equal to t and lower limit, and we have negative sign also, so negative negative positive, and e raised to 0 which is 1. And if we put t equal to infinity, we have e raised to minus infinity, limit of 1 is 1, and because e raised to minus infinity is 0, we have 0 plus 1, that is 1. So therefore we have shown that value of gamma function at n equal to 1 is always 1. So we are just putting n equal to 1 here, and after integrating we obtain that value of this improper integral is 1. So gamma 1 is always 1. We discuss now other forms of gamma function. Gamma function can be represented in terms of this improper integral also. So if we want to prove this improper integral, then we can we want to show that this is nothing but integral from 0 to infinity e raised to minus x, x raised to n minus 1 dx. This is definition of gamma function. So if we observe, we require e raised to minus x term here, and there is no e raised to minus x term here. So from this we can have the idea that here we have exponential function, so it is e raised to minus x square, but we require e raised to minus x. So from this we can have the idea that we should consider the change of variable. If we change the variable from x to some another variable, say y, then we should consider x square equal to y. If we change the variable from x to y by taking x square equal to y, then we will obtain this type of term, e raised to minus y. So we will start from right hand side, and we will show that right hand side is nothing but gamma n. So in right hand side we change the variable from x to y by the relationship x square equal to y. So if x square is y, then x is nothing but square root of y, or y raised to 1/2. So therefore dx by dy is nothing but 1/2 y raised to 1/2 minus 1. So therefore we can replace dx by 1/2 times y raised to minus 1/2 dy. And limits, we can check limits of y. Lower limit of x is 0, so for x equal to 0, y is 0, and upper limit of x is infinite and y is x square, so square of infinity is infinity. So we have to write limits also as x is 0, y is 0, and when x is tending to infinity, y is tending to infinity. because everything we are changing in terms of new variable y, so we have to take care of limits also. So now therefore right hand side becomes, first we write down the right hand side is 2 times 0 to infinity x raised to 2n minus 1 times c raised to minus x square dx. So there is no change in the limits, so we keep limits as it is, and instead of x we have to put y raised to 1/2. Okay, because x square is y, then x is y raised to 1/2. So we have y raised to 1/2 to the power 2n minus 1, x square is minus y, and dx is nothing but 1/2 y raised to minus 1/2 dy. So now we can see this 2 will cancel out with this 2, and this power of y we can rewrite as y raised to n 1/2 into 2n, that is n, minus 1/2 e raised to minus y and y raised to minus 1/2 dy. So if we combine power of y raised to n minus 1/2 minus 1/2, so that becomes n minus y. So we have y raised to n minus 1 into e raised to minus y dy, and this y is dummy variable, so either we write x or y, does not matter. So we replace y by x and we obtain this. Okay, because we know that if we consider integral of fx dx or fy dy, okay, because whenever we have definite integral, this variable becomes dummy variable, so either we can use x or y. So same thing we are using here, we can replace y by any other variable, and if we observe, we obtain this is nothing but gamma function of n. So this is another form of gamma function. We have written that gamma n is 2 times 0 to infinity x raised to 2n minus 1 e raised to minus x square dx for positive real number n. So you can be asked to prove this type of relationships using definition of gamma function. We are just changing the variable from x to y. We are taking x square equal to y, and then everything we are converting in terms of y, and we obtain that this is another form of gamma function. So this can also be proved. We can show that gamma n can be written as integral from 0 to 1 log 1 by x raised to n minus 1 dx. Here we have 1 by x, so you can see for x equal to 0 we have 1 by 0 infinity, so this is improper integral. And if we want to prove that this is nothing but gamma n, here also we have to take change of variables. So we can compare with gamma function. Definition of gamma function is e raised to minus x raised to n minus 1 dx. So from this, if we compare these two integrals, we may have the idea about change of variables. So here power of log 1 by x is n minus 1, and here we require power of x as n minus 1. So this suggests us to take the change of variable using this relationship. If we consider log 1 by x equal to y, then we will obtain y raised to n minus 1 here, and after converting x in terms of y, we may have this type of exponential function. Okay, so from this we can have the idea that which type of change of variables we have to consider. So here also we will start from right hand side. We change the variable in this way. We consider logarithm of 1 by x equal to y. Then by the definition of logarithm we have 1 by x equal to e raised to y, and therefore if we take reciprocal it is x equal to 1 over e raised to y, that is x is e raised to minus y. And if we take derivative of x with respect to y, we have minus e raised to minus y. So dx will be replaced by minus e raised to minus y dy. So log 1 by x is replaced by y, dx is replaced by negative of e raised to minus y. And now we talk about limit. Lower limit of x is 0. So when x is 0, we can use this relationship to decide value of y. So when I consider x equal to 0, I have log 1 by 0, which is infinity, and it tending to infinity. So when x is 0, y is tending to infinity. So the limit of y corresponding to x equal to 0 is infinity. Upper limit for x is 1. So if we put x equal to 1 here, y is log of 1 by 1, that is log 1. So we obtain 0. So limits of y are from infinity to 0. So now using all these things, let's see what our right hand side becomes. Right hand side is 0 to 1 log of 1 by x raised to n minus 1 dx. Okay, so when x is 0, y is infinity. When x is 1, y is 0. Log of 1 by x is y, and dx is negative of e raised to minus y dy. So this we can rewrite as minus infinity to 0 e raised to minus y raised to n minus 1 dy. We have taken negative side out of integral. And as we know the property of definite integrals, if we change the limits, then these two integrals are negative of each other. So if I want to omit this negative sign, I can change the limits. So if I change the limits, I will have 0 to infinity, and I replace y by x. It is dummy variable, so it does not matter whether I write x or y. So we obtain here, this is nothing but gamma function of n, and this is what we wanted to prove. So these are the simple exercises. We can represent gamma function of n in various forms. So all we have to decide is appropriate change of variable. So what we can do is we can compare given integral with definition of gamma function, and from that we will have the idea that which type of change of variable we have to consider. Like this, here we have log 1 by x raised to n minus 1. So we can consider comparison with x raised to n minus 1, and from that we obtain the idea that we can select log 1 by x equal to y. In earlier example, we had e raised to minus x square into x raised to 2n minus 1. So if we compare with definition of gamma function, here we require e raised to minus y, and here we have x square. So this suggests us to take this change of variables x square equal to y. So in this way we can prove this various we can do this type of exercises related to gamma function. So this is all about today's session. In next session we will discuss properties of gamma function, and we will see how those properties can be used to evaluate certain type of improper integrals. So I hope you like this lecture. Thank you very much.